So yes, so today my presentation will be really focused on the technology side. So I will present our two patents, OFCEAS spectroscopy and low pressure sampling, and how we can apply it to SEMS. Okay, so first there will be two presentations of the two patents. Then we will talk about what we can measure with it today, and then we will focus on the SEMS application and then a conclusion. First, our first patent, the optical part, OFCEAS. You don't need to remember the entire name, but it means optical feedback cavity enhanced absorption spectroscopy. Basically, it's a laser technology. So that's what you have inside the analyzer. So you have the laser, you have a set of mirrors, you have a measuring cell, and you have a detector. You have the gas or your emission gas going in and out of the measuring cell, and you send the beam of the laser inside the measuring cell. You have an interaction between the light and the gas, and then the remaining light is going up to the detector. The first particularity of the OFCEAS patent is what we call the enhanced cavity. So when we send the beam inside the measuring cell, we will have an enhanced cavity. So we will try to keep the light as much as possible inside the cell. So when we talk about FTIR and DIR, we have, I would say, quite simple cell. So we will keep the light from 1 to 10 meters for most of the available analyzers available on the market. And when you have a high reflective cell, you use high reflective mirrors, and the goal will be to keep the light from 10 to 50 kilometers inside the cell. And as we use Berlin law, the longer is your path length, the more absorption you have. So this is really why we will go in the measurement of PPT and PPB concentration, when a normal FTIR and DIR will be more in the percentage and ppm concentrations, because we will have 5,000 times more absorption. So that's the first part of the OFCEAS patent, the enhanced cavity. And then now we move to the second part, what we call the feedback effect, optical feedback. So that's really part of the patent from the University of Grenoble, who own the patent of OFCEAS. The OFCEAS, so the feedback effect, the goal is to play on the laser. When you have a normal laser, the beam of your laser look like on the left side. So you have a large beam. This is the wavelength you want to inject, and then part of the energy of the laser is used to create noise on the side of the wavelength you want to inject. When you have the feedback, you have a boost of your laser. So most of the energy of your laser is exactly of the wavelength you want to inject. So you have a very intense peak, but also a very sharp peak, because you have less noise on the side of this beam. So we have very high resolution of this peak, and we have a very intense peak. When we do a measurement, we tune our laser by changing the current, and we generate 200 phenomena of resonance to obtain 200 very intense peak of light. Then we obtain a spectrum. So if there was no light, we will have 200 points here straight, but because there is a gas here, we see some peak of absorption. And by doing the integration, we can have the absorption peaks of this gas. And what is very important is the resolution of the spectrum. So the full spectrum is 0.2 nanometer, and between each peak, you will have 1 picometer. So just to give you an idea about what we talk about resolution, imagine we are in the infrared. We want to measure, for example, H2S in a gas with water and in CO2. Then the NDIR resolution is 20 nanometer. So if you want to measure this H2S in green, at the same place you have some water. So most of the NDIR will use maybe a cooler to remove this water to avoid the cross interference. FTIR, you have a resolution of 2 nanometer. So the H2S, the resolution is better, but still you have some water at the same place. And with the OFCEAS, you are like a microscope. So you do like a zoom, and you go in a region where you see separate peaks from each other. So you have your H2S peak here, CO2 peak here, and water peak here. So the goal is to have a very high resolution to obtain separate peaks, and also to avoid cross interference with greenhouse gas present in your matrix. So when we are talking about emission, we could have CO2 in percent, water in percent, or even methane in ppm range. One of the other aspects of the high resolution is that we can find in our spectrum what we call a spectral zero, so a place on the spectrum where the light we have sent is received. And we will use that to do a zero on our measurements. Every measurement, we will have a zero information in the spectrum. And as I would say, a safety feature, we also control every time the only changing parameter in our measurement, which is the cleanliness of the mirrors. So we do our 200 points, then we shut down the laser, and we calculate the ring down to know what is the path length inside the cell. If we have some loss of reflectivity of the mirrors over the time, then we will be able to adjust, to calculate the loss of path length, and then to adjust the measurement. So we avoid the drift based on the, I will say, dirtiness of the mirrors. And we can also put an alarm on this parameter. So you can call a technician to clean them at site if you need to do it. In every analyzer, so the standard analyzer will be a rack 19-inch, and in each analyzer you can have 2 cells, and each cell can have 2 lasers. So in one box you can have up to 4 lasers. And for emissions, we would have from 1 to up to 10 gas in one rack, and we can combine the racks if needed. So just a quick sum up about the OFCEAS part. The advantage is to be able to measure from ppb to percentage concentrations. We do a direct measurement with high resolution to avoid the cross interference. We have a multi-gas solution, so one analyzer can measure several gases. And we control the zero information and also the cleanliness of the cell to avoid drift of the system. So I will now move on to the second part of the patents, the LPS, or low pressure sampling. So this is an EP3 patent, and this is very useful when we talk about emissions. So basically, imagine you have your stack with your gas inside. Then inside the stack, we will apply an inlet filter and a sonic nozzle. So it's a critical orifice of 50 to 200 micron. Then we will have our sampling line, which in most of the case will be heated. The sampling line will go up to the inlet of the measuring cell, which is also heated. And then the exhaust will go up to the vacuum pump. The gas is going through the sonic nozzle up to the measuring cell, and then up to the vacuum pump. From the moment the gas is going through the critical orifice or through the sonic nozzle, we will work in low pressure sampling. So we will apply a pressure between 20 to 100 millibar absolute. It's really important. We are talking about absolute pressure. Why do we use low pressure sampling? Because low pressure sampling has an impact on the shape of the absorption peaks. So here, for example, we still have this H2S measurement in a gas matrix with a lot of CO2 and methane, for example. And we have the absorption spectrum at different pressure. So in purple, you have the absorption spectrum at 800 millibar absolute, and in blue, at 100 millibar absolute. What we see is when we lower the pressure, the peaks, they are getting separate from each other and a little bit smaller. So the goal when we reduce the pressure is to avoid the cross interference between the peaks. So for example, those two peaks are one at 800 millibar, and when they are at 100 millibar, they are separate from each other. So just to give you a live, and I hope the window will work, a live simulation. Here we are measuring H2S in biogas application. So we have our H2S peak on the left side. And then if we remove the sonic nozzle and go back to atmospheric pressure, then we can see that we have cross interference with methane and CO2. If we go back to low pressure sampling, we will be able to see again our H2S peak and our two CO2 peaks here. So that's really, I think it's a very good example to see the advantage of the low pressure sampling in terms of cross interference with greenhouse gases. Second advantage of the low pressure sampling is when you reduce the pressure, you also reduce the dew point. So imagine you have so here we have a table with dew points, so we can have different concentration of water, so 10 to 40% volumic, and different pressure. So imagine we are in, I would say, more incineration configuration, where we have around 30% volumic water. At the analyzer, we will apply around 50 millibar absolute pressure. Then our dew point will be at 13 degrees. At the probe, after 30 meters, we could be at 100 millibar because we have a loss of pressure around the sampling line. But still, our dew point will be at 24 degrees. And imagine we are, I would say, in a large refinery plant where we have a very long sampling line, 80 meters. Then still after 80 meters, we are able to maintain 150 millibar absolute, and our dew point is at 31 degrees. So really, when you lower the pressure, you avoid the dew point. You will have also similar phenomena with salt formation, HCl and ammonia, for example. So in general, we will recommend to heat our sampling line at 80 degrees to be always way above these points, but still, to be able to avoid water dew point and acidic dew point. Few other advantages. When you give me 1 liter at atmospheric pressure, if I work at 50 millibar, it's 20 liters. So we will work with very low flow analyzer. So for SEMS, the standard will be around 20 to 24 liters per hour. And for process monitoring, it will be between 3 to 14 liters per hour, which means we will also sample less dust from the process. So you will have less filter pollution. And we also create an expansion of the molecule inside the sampling line. So you have faster transfer time from the measuring sampling point up to the inlet of the analyzer. And finally, we have a very small cell, 30 milliliters. So the time to refresh it is much faster than a large cell of 1 to 2 liters, for example, for FTIRs. So you have a faster transfer response time also of the analyzer. So that's also the end of the second patents. Just a quick sum up of the benefits. LPS, we can reduce the shape and change the shape of the absorption peaks. So we avoid cross interference, and one laser can measure several gases. We have a very small cell, which means we have a fast response time of the analyzer. We have a fast transfer time. So the overall response time of the system is faster. We reduce the dew point, so we limit the need of high temperature for sampling lines, and we don't use gas cooler. It's a hot wet technique. And we have a low extraction flow, which means we have less filter pollution. So I will now go to the analytical possibilities. So what can you measure with these two patents today? We can measure around 30 gas species. We were one of the first to measure, for example, hydrogen with infrared technology. But we also measure most of the gas needed for SEMS, so NOx, ammonia, H2S, formaldehyde, HCl, HF, CO2. And this technique, as we are not affected by the background, can be used in different applications. It can be used for trace measurement in pure gases, for example, hydrogen purity, but also for trace measurement in natural gas or in emission. So that will be the same technology, same gases, and also most of the time we will go from ppb or ppm concentration up to the percentage concentrations. And in terms of integration, the standard will be a rack mounted each, but we now have a more industrial integration, like wall mounted units, ATEX Zone 1 system, EXD and EXP, and also ATEX cabinets. So now we will go to the application and continuous emission monitoring. Yeah, I will just go to the next slide. Continuous emission monitoring. So you have your stack. We have a specific probe that we have designed to be sure that we keep the sampling line at the correct temperature up to the analyzer. So you have a probe where you have inside the stack and heated by the stack or heated by the system, the sonic nozzle and the inlet filter to avoid salt formation at the sonic nozzle. So your sonic nozzle will be here, then your sampling probe is going up to a sampling box where you can have the option to backflush automatically every day, this probe. Then you have the heated line, 80 degrees, and your analytical cabinets with 1, 2, or 3 racks, and your vacuum pump. And this system is now Qual1 certified by TÜV and by MSAT. So there is a already validated certification, and there is a pending certification. So just a quick example of some benefits of the system for continuous emission monitoring. First, you have a multi-gas analyzer. So, for example, here we have a picture of a cabinet with 3 control points. So 3 different stacks in one cabinet with 3 times 30 gases, 10 gases control. So in the entire system, you control 3 stacks with 10 gas. Sensitivity, we go down to ppm, ppb measurement. For example, ppb will be HCl, HF, formaldehyde measurement in the stack. We have a high selectivity, so we limit the interferences, especially with water, CO2, CO, and CH4. We use low heated line at 80 degrees, and we are a hot wet technique, so we don't use gas cooler. We have low maintenance pump, so the main spare parts will be filters, inlet filters, and pumps, like membranes of the pump and filters of the pump. And the system can be available in ATEX version. So we today we have a certification from TÜV for 7 gas, but we will go next year with a new certification with the new gases like NO2 and HF. So this is our actual certification with very low range, for example, for NO measurements and ammonia. And the goal is to go even better, to be even better next year with a very low range for CO at 30 milligram, low ranges for NOx, NO and NO2, and a very low range also for HF at 1.5 milligram range, certified range, and methane also. And the goal is to be prepared for the future if the regulation will require to lower more and more the emission limits. So if we compare our solutions compared to I would say in the case of incineration of FTIRs, then we see that for example for NO2 our next certification will be 30 milligram. And for FTIR, the lowest range is 50 milligram. For HF, it will be 1.5 milligram when the best FTIRs are at 3 milligram. Methane will be at 5 milligram versus 7.5 milligram for FTIRs. And for CO, we will be at 30 milligram when most of the best technology at the moment are at 75 milligram. So about the maintenance for emission, as I told you, there is a limited need of maintenance. The main consumables will be the inlet filters, the pump cartridge, and the pump membrane. We use lasers that are used, most of them are used in telecommunication. So their lifetime MTBF is between 8 to 10 years. Our pumps are given by our German manufacturer around more than 4 years. And sonic nozzle, it's I would say a steel tubing, so it's quite resistant also. And for more current installation, we can say that the maintenance cost compared to a standard FTIR is around 30 to 50% of the FTIR cost. So we hope to have a very a competitive solution in terms of operating costs. So just a few images of current installation where we compare measurement of ammonia and FTIRs, of OFCEAS and FTIRs on the same stack. So here you have the measurement of ammonia and in an incinerator. In blue, you have the laser SEM. What we see is really the response time. So you have sharper peak when the FTIR will have, I would say, more like an integration over time. And the peak is detected before with the laser SEM. Other values with HCl, and what will be interesting is the HF value. This is really why we try to certify a very low range for HF. Here you have the continuous value around 0.08 milligram of HF in the stack, and with the FTIR you just have a flat line because you are really at the limit of the technology, and really you see that only the OFCEAS can see such low concentrations in the stack. So yeah. Some more example where we always see that the laser SEM is faster than the FTIR. Yeah, stability. Yeah. I think I don't have the time anymore. So just a quick conclusion. With the laser SEM and the use of our two patents, we try to look at the smaller to be the smallest ranges certified on the market because we want our customer to be prepared for the future. When we know that the authorities will go more and more for lower limits. And we also know that when you buy an instrument for controlling your stack, it's a long-term investment. So you want it to be compliant for many years. And also we try to be a smart technology by lowering the operational cost with low heated line. So you will use less electricity to heat your sampling line, and to have less consumption of instrument there and low maintenance in terms of consumables and site maintenance needed. So the goal is to reduce also the operational costs. And for sure, we are a new technology, so at some point we are also seen as a bit expensive, but you should also compare the operational costs with the CapEx to be sure to have a clear picture when you use OFCEAS to see that you will save also some money on the long term. So thank you for your attention. I hope I am on time.
Thank you very much, Étienne. I think more or less. I'm looking at the questions and chat tabs and can't actually see anything that's come in. So I'll keep an eye on that just for a moment. Am I right in thinking that you don't really have to calibrate these systems? Is that correct?
We calibrate it in our lab, and then we deliver it at site. When we talk about emission, it's you need to calibrate it as a regulation asks you to do it. But technically, for other markets, like when we work for purity of gases or for ambient air, some of our customer doesn't really calibrate it. And if you come to site with reference gas, after 3 years, you are still in the good position. Yeah.
So you're only using reference gas because that's the requirement.
Exactly.
You don't feel you actually need it.
No, yeah. If you don't have major maintenance on it, no.
Yeah. And in your Core 1 targets, I noticed that NO monoxide is still at 78, I think it was, milligram per meter cubed. Is there any reason that's not being brought down further to be more in line with the NO2?
I don't know. I can ask to our product manager, but I don't know. Yeah.
Great. And you always measure water, of course, because it's a wet measurement effectively, even at low pressure. Yeah. That's fab. Thank you very much for that.